Welcome to lecture 15, where we're going to talk about splines and piecewise interpolation. As a review, last time we talked about issues that we might have with polynomial coefficients for interpolation, and we looked at, say, Newtonian interpolation or Lagrangian interpolation. Within that, we then talked not only about interpolating, but then the dangers of inverse interpolation and how we should recast that problem as a root solving problem. The big issues that came up with polynomial interpolation was that we couldn't deal with extrapolation. And more importantly, for what we're looking at, is we can have large oscillations within our data when we try to fit high-order polynomials to relatively few data points. This is where splines and piecewise interpolation are going to come in. In piecewise interpolation, of which splines are a specific type, we're going to break up the entire line into several different subpoints. We're going to use the information only around those points to get a good interpolated value. So today what we're going to cover is what is a spline. We'll start by talking about linear and quadratic splines, then we'll get to cubic splines, including the different types of end types that come with cubic splines, specifically natural ends, clamped ends, and not end conditions. We'll then touch on lookup tables and how we can use these to get data from our systems. Lastly, we'll talk about inbuilt MATLAB functions for piecewise interpolation, and then we'll touch briefly upon multi-dimensional interpolation. So the first question you're probably asking is, what is a spline? Well, in a non-mathematical sense, a spline is a thin piece of wood. Splines came about as originally drawing tools for helping people draw curves, as illustrated on this left-hand side. What would be done is a thin piece of wood would be held in place on two different ends, then points would be added along the curve. Points would be added, and then the wood bent around the curve, around those points. Then a line could be drawn along that piece of wood, along the spline, to generate a complex shape that's going to interact exactly at each of these points or knots. Where this was originally used a lot in math were to draw complex functional forms. What they would do is they would take these leaden weights, or called ducks because of their duck-like shape, that were attached to this thin piece of wood. And they would be held in place at each of these points that can be called either pins or knots. Through this way, we can get very nicely shaped curves to be drawn without having to do, without some of those bizarro oscillations that we would get with high-order polynomial fits. As you remember, if we had a 1, 2, 3, 4, 5, a fifth-order polynomial fit, out at these edges in this curve, we would get wild oscillations. But here, using this spline implementation, we get a nice continual curve. So these can be very useful in fitting complex lines. Let's look at this a little bit more in detail, where we compare different ordered polynomials to a spline line. So let's take a step change function shown in black. So here I have my step change function, and let's say I want to go in and take several different points along that line to get, say, a third order polynomial. Using a third order polynomial, I need 4 points. So let's take a point here, 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 and here. When I fit that polynomial, we can see that I have curved points out in the flat regions and this very long sort of slope over the whole segment. If I want to sharpen this, the line around that x equals 0 point, I need to add in more points that I'm fitting. So if I go out to a fifth order polynomial, I get a sharper edge to my function at that fit. but I end up getting these spurious oscillations out at the end. And we continue to see this as I add more and more points. I get a sharper line around 0, but I get larger oscillations at the extrema. A spline is going to say, I'm going to only look fit around me. So if I take, say, a first order spline or a linear spline, I can connect each of these, I can connect between each of these points. Even in this case of having 8 points that I'm fitting to, I can perfectly match the flat pieces at the end and the beginning, and I get a relatively sharp curve in between the 2 points. So we can see already that this spline is going to hopefully get us closer to the true functional fit by doing interpolation only in the location of my data points. Let's put this more into an algorithmic approach that we're going to use for numerical methods. So what we're going to do is, instead of fitting one n-order polynomial, we're going to fit multiple low-order polynomials in a piecewise fashion, so segment by segment. By fitting these individual pieces, we can minimize the negative effects of large order fit polynomials due to oscillations. These interconnecting polynomials are called spline functions. So each of these pieces is going to be called a spline function. So in essence, these spline functions are going to minimize our oscillations and therefore reduce round-off error reduce the round-off error due to those low-order nature. So we're going to get a much smoother fit and more accurate fit, at least hopefully. So let's start developing this. First, we need to break our spline or the segments into several different subintervals. Our spline function, usually written as this S term, is going to operate over multiple intervals. So each of those intervals is going to be broken up by individual data points over which we operate. I'm going to refer to which interval that we look at by this subscript on the S. Right? So in this case, if I have interval 1 between my first data point and my second data point, it gets referenced to as S sub 1 of X, because it's working on interval 1. I end up having n minus 1 intervals for n data points. This is because I always have one less interval than the number of data points that I have. So the number of data points used for each spline is going to be dependent on the order of my spline. So if I only use 2 data points, that's a first order spline. I could use multiple intervals to fit a curve, and that's going to increase my order. So let's talk about our different order types. The easiest one is obviously a first order spline. This is shown here. In this case, I essentially draw a straight line between each of my points. I have a linear fit between every single one. The key set to that, the key argument that we have to fit our line to is that each interval must go through each point. Right? So if I'm fitting this interval, it has to go through the 2 endpoints. Same thing here, same thing here. My second order spline is going to fit a parabolic equation between pairs of points. So we're still only going to fit on this interval on these 2 points. So we still have that requirement that we go through each point. But this isn't enough information to fit a quadratic equation. What we're going to do is say that at an interior point, so say this is an interior point or that is an interior point, not only do my function values have to match, so f of x, 1 must equal f of x2, or my spline 1 has to equal spline 2 there, but the derivatives must be equal. Okay, so my derivatives at each of these interior points from the two intervals have to match. The last spline order that we're going to talk about is a third order spline, where we're going to find a cubic equation between pairs of points. Here we say that we have to not only go through points and that the first derivatives have to match, but we also say that my second derivatives have to match. The key point, though, is we're going to have two types of cubic, or multiple types of cubic splines, because how we deal with these second derivatives is going to be a little bit different depending on which type of spline we're looking at, based on what we're going to do at the endpoints. We'll get to this in detail in the next class, but today we're going to just focus on these two types of splines. The first spline, of course, is our linear spline. And our rule is going to be that on each interval, for each interval 1, 2, 3, my points, I have to go through both of the points of data. So what we're going to do is set up an equation that's going to tell us what's going to happen. Here we have my spline, my first order spline, where the first interval and the second interval, notated by S1 and S2, must be equal to each other at xi plus 1, right? So at this 2 spot, I have to be, the values have to match. And within that interval, I'm going to use Newtonian interpolation. So if you remember back to interpolation, we can say that f1 is equal to fx1 plus f of x2 minus f of x1 all over x2 minus x1 times x minus x1, right? So this is going to give the equation at those 2 points. We can put this into a spline type format by saying Si of x is equal to f of I plus f of I plus 1 minus fi over xi plus 1 minus xi times x minus xi. Right? Here we have the points that we're, specific points that we're fitting and our various intervals. Let's put this into some sort of practice for the case illustrated here. Here I have a series of x's, a series of f of x's, so x are f of x's, and we can pull out our various orders. So let's look at what's going to happen when we are looking for x equals 5. The first thing to do is identify which interval we want to operate on. In this case, 5 is sitting between 5 is between 4.5 and 7. So this means it's sitting in our second interval. Remember, this is our first interval. This is our second interval. So we're sitting in our second interval case. So if I pull up the equation, we know that we're dealing with that second interval. So I can put in an S2 of x here, and we can now go through and fill in the appropriate i's. Remember, we're going to actually keep track of the different i's that are going to go in here. So in this case, we need F2. So I'll put in a little F2 here. So what's our second F? Well, it's a 1, 1.0. Now, I need this term, which is fi plus 1. Well, that's the third term, so that's 2.5 minus fi, so that's f2, right, because we have that 2 here again. So minus 1.0 all over xi plus 1. Well, what's the next xi plus 1? That's 7.0 minus xi, so x2, that's 4.5 times x minus xi. What's my current x2? Well, that's 4.5. Right? Now we have the basic form of our equation, of our linear spline. Now we just have to go in and calculate this at 5. So we can just copy down most of these terms because we've already solved them out, or punched in rather the correct terms. Now I put in a 5 for x, and if I do all this math, I get 1.3. Right? So this is this would be the answer for my equation. Right? Gone through. We've figured out which interval I'm operating on. Right? We're operating on this interval right here. We've built the appropriate spline form for our second interval, and then we can go in and calculate out for our individual x's. Things are going to get a little bit hairier here now that we're moving on to quadratic splines, because not only do we have to go through each point, but we have to have matching first derivatives. Right? These are going to be the characteristics of our quadratic spline or second order spline. Once again, we're going to need to think about our different intervals. But unlike before, we're going to have to consider the entire range over which I have data, rather than looking only at the one specific interval I'm interested in. This is going to be because we need to locate those first order derivatives, right? I need information about both of these 2 points in order to make my match go. So let's put these 2 requirements into a mathematical form. We can see that we have our second order spline between our first point and our second point need to match. We can also say that the first derivatives need to match as well. Right? So just putting some mathematics into this form. We can now bring out an equation for our second order spline function. So 2 comma I of x is going to be some a I plus bi times x minus xi plus ci times x minus xi squared. Right? So we can see where we have our linear piece, just like we had for a linear spline, and now we're adding in this quadratic piece for a spline. So if I go and I write this out or I generalize this, I can say that my second order spline for any interval is going to be the series of coefficients a1, a2, a1, b1, c1, a2, b2, c2 times some whatever our x is, as long as we lie in that particular interval. If I look at this data series, though, we now have multiple unknowns. Right? I have 3n unknowns for each data point. Right? So each of these is representing one interval, one set of data points. I've got 3n unknowns. I can no longer just nice, easy peasy solve this out like we did with the linear spline. We now need to go through and start considering what else we know about these equations. So let's first consider the fact that we need to go through each of the points. So I can use this top requirement to write out this equation. So I can take this equation that we're going to go look at and plug it into this top equation. So here we have f of I plus bi xi plus 1 minus xi plus c1 xi plus 1 minus xi squared. So let's say we were looking at these 2 points, right? If I'm talking about f1, I'm going to do the matching here at x2 and f2. Right, so this part of the equation would give me the value shown there circled in blue. I then want it to equal the spline piece coming from this spline highlighted in red. So the equation for that spline is fi plus 1 plus bi plus 1 times xi plus 1 minus xi plus 1. Remember, we're always taking the xi that I'm dealing with for that order minus the x where I'm looking. So this is the point matched with fi, and then this is the point of interest. Right? So I have fi plus 1 plus bi plus 1 times the quantity xi plus 1 minus xi plus 1 plus ci plus 1 times xi plus 1 minus xi plus 1 squared. What you'll immediately see is that these terms cancel out, right? They go to 0. So if I go ahead and write this out, these terms don't need to be included. We're going to see come up, or we're going to see a few things come up often. So we're going to see this term where I have xi plus 1 minus xi. We're going to write this as hi, just to save us a little bit of handwriting as I go through this procedure. So if I substitute this in here, I end up getting fi plus 1 plus b1 hi plus ci hi squared plus equals fi plus 1. Here, once again, we're just using a little bit of shorthand. So when I do this, I end up getting, if I were to count out how many times I can do this, I can get 2n equations, right? So this is good. We're moving forward towards addressing the need to having 3n unknowns. However, this does not give us 3n equations. What we need to do is use that second piece of information we know, that the derivatives must match at each interior point. So what we can do is we can take our equation and take the derivative. Here I've written this out. You'll see that the fi's go away. We get rid of this minus xi, and we can have 2ci times x minus xi. So this is going to be our derivative equation. Just like before, we can take the piece from, say, this spline interval on the left and look at it, set it equal to what's happening to the spline interval on the right. So we can say that the derivative of the spline at x must be equal to bi plus ci times x minus I. And that has to be equal to bi plus 1. Let me write that a little bit neater. Bi plus 1 plus ci plus 1 times xi plus 1 minus xi plus 1. Right? In all of these cases, we're going to see that these, oh, there they are. This is going to be equal to each other. So we're querying what's going to be the derivative at this point from the left-hand side, and then what's the derivative from the spline on the right-hand side, both at this xi plus 1 point, and we're going to force them to be equal. Using the shorthand from the previous slide, we can put in hi into this subtraction case, and this term with the xi plus 1 minus xi plus 1 obviously goes to 0. So this is going to give us n minus 1 equations based on the derivatives, if I count them all out. So if I look in general, we have n, 2n from our continuity, so what's happening with the points, so using this equation, and we have n minus 1 equation from setting the derivatives equal to each other at the interior points. We still need one more equation. So what we will do is we're going to set the derivative of my first knot to 0. So we're just going to say arbitrarily that my derivative, which is represented by that constant C1, is going to be 0 at that first knot. So we're not going to have, so this is just going to give us that one last piece of information, bringing us up to 3n equations. So now we have a series of equations that we can work with. So these three equations are going to be the equations for fitting a quadratic spline. And we're going to have to solve them simultaneously, right? We have unknowns in the bi's and c's. We know the x's, we know the f of i's. We need to do, we need to put in all the data, and then we can do linear algebra to figure out what those b's and c's should be. Let's do an example, and let's look at the exact same example that we had before, but this time we're going to fit a quadratic spline. So once again, we're going to look at x equals 5. Here we have our x's and our f of i's, same points. Unlike before, we can't just go into this second interval. I actually have to go through and use all of those equations. So we're going to need to solve all of these equations together before we can go in and use this information. So let's split up our data into our different intervals. So here we have our different fi's, which I'm just pulling from over here. Now I can start employing my continuity and derivative equations based on 1, 2, 3 intervals. So we can pull forward our continuity equations. Here, I've written them at the bottom. We can look at that first interval set where we have f1 plus b1 h1 plus c1 h1 squared equals F2. Here, remember that C1 equals 0. So if we were to look down in this term, that H1 squared goes away. So I've just saved some time by not writing that one out. Right. So then on our second interval, we have F2 plus B2H2 plus C2H2 squared equals F3. And then finally, on that third interval, we have F3 plus B3H3 plus C3H3 squared equals F4. Right? So now we just need to go through and calculate what each of those H's are. In this case, I'm just going to go through, look at those different X's and subtract the 2 off. In the first case, we take 4.5 minus 3, set that equal to 1.5. Right? That's how wide these 2 points are away from each other. H2, we take the next interval pair, 7 minus 4.5. That's going to give that distance of 2.5. And then we can look at that last interval pair, so 7 and 9, giving us a distance of 2. Right? So if I now sort of go back and look at these equations, let me change color here. We know F1, F2, F3. We know H1, H2, H3, and F2, F3, F4. So the only things we don't know are these B1s and 2s, 3s, and C's 2 and 3. Right? So not enough. We have 3 equations, 5 unknowns. Not enough. We need to turn to our continuity of derivatives using this equation down here that says that B1 is equal to B2. Where this is coming from is on our first interval, remember, C1 is 0. So we have B1 plus 2 times 0 times H1 equals B2. So we just get B1 equals B2. And then we can do the second interval that we're going to look at, which is B2 plus 2C2 H2 equals B3. Okay, so now this is going to give us 5 unknowns, so B1, B2, B3, C2, C3, and 5 equations, 1, 2, 3, 4, 5. Okay. So we have all these equations, we have our unknowns, we can now take this and put this into some sort of matrix form. I've done this, I've pulled forward all those equations that we just talked about. I can now go in and enter them one by one into this, into a matrix. I know F1 is 2.5, I know F2 is 1, and I know H1 is 1.5. If I plug those numbers in, we'll find that we have 1.5 from H equals negative 1.5, or in other words, 1 minus 2.5. Right? I can do the exact same thing with each of these equations where I plug in my knowns for F and H into the equations to form this matrix. I'm not going to go all the way through forming this matrix because hopefully you are well familiar with forming these matrices from our discussions on linear algebra. But suffice it to say, when you punch in all the numbers and you put it into the matrix form, we end up with this matrix shown here. At this point, all that's left to do is solve for my constants B1, B2, C2, B3, and C3. We can use any of the techniques that we had previously talked about, whether that's Gaussian elimination, LU factorization. We're using MATLAB's built-in functions such as back division to solve for B1 to B1, B2, B3, C2, and C3. When I do that, I will find that B1 is -1, B2 is -1, B3 is 2.2, and C2 is 0.64, and C3 is -1.6. Remember, there's that secret C1 is oops, C1 is 0, right? Just by definition of us setting that initial knot to 0. Now we can take these coefficients and my equation for my spline and punch them in. So my S1 is 2.5 minus 1, right? So this is our B1. This, remember, was our F1. So F1 is 2.5 minus plus B1, which is -1, times X minus X1, which is 3. So that first spline function is 2.5 minus X minus 3. I can do the same thing here, where I pull in my F2, I pull in B2, I pull in X2, I have my C2 and my X2 here. And then we can do the same thing for X3. Sorry, S3. So we can use these equations we can use these coefficients that are coming out of my linear equations to solve for my spline. Now that we have my spline intervals, we can go back to the problem that we were originally trying to solve, which is asking what is the value of f when x equals 5. So here we have my intervals again, my spline intervals. We need to go back in and identify which interval I sit on. So x does not sit between 3 and 4.5, so it's not in the first interval, but it does sit between 4.5 and 7, which means we're sitting on the second interval. This means the spline that I'm looking for is the second order spline. So I can pick out this equation, plug in 5, and when I do, I'll get 0.66. So hopefully this has gone and shown you how we can, the steps that we need to take to fit a quadratic spline and then solve for it. These are a little bit more complicated than our linear splines because we actually have to go in and solve for the spline over the entire region, because we need to use the linear algebra over the entire region in order to get all of my coefficients. Only at the end do we then go in and pick our specific interval to punch 5 in. The last type of spline I'd like to talk to you about are cubic splines. In general, we could use many orders of magnitude splines as we have number of data points. However, cubic splines tend to be the most commonly used. This is because they provide relatively simple representation and have desired levels of smoothness. In comparison to linear splines, the linear splines tend to have discontinuous first derivatives, right? We have this sort of sharp jumps at each of the points. Our quadratic splines overcome that, but then are discontinuous at the second derivatives. Cubic splines are going to overcome that. If we were to go even higher to quadratic splines, we tend to have instabilities leading to oscillations and therefore poor fitting curves. So let's look at these cubic splines. Just like before, we're going to have the ith interval be made up of this linear piece, a quadratic piece, and then we're introducing this cubic piece with a coefficient of d1. We're going to end up having n-1 intervals for n data points. And because we have n-1 intervals, and we have 1, 2, 3, 4 unknowns, we have n times n-1 unknowns that we need to evaluate. So let's look at the types of conditions that we're going to use to set up these equations. Here I've put the equation for the interval. So the first series of effects are going to be the same as quadratic splines. We're going to say that at point xi plus 1 on the ith interval, it must be equal to the function value at I plus 1. Right? So if I'm using this interval, this point must match the point at this interval. So same thing that we had on the previous, for the previous splines. We're still going to say that we have to have continuous first derivatives at each interior point, meaning that my derivative on the two intervals must be the same. We can write that out in the same fashion that we had before, adding, of course, our d term. The third consideration is we're going to say that at each interior point, the second derivatives must be continuous. So written mathematically, the second derivative of my ith interval at xi plus 1 must be equal to the second derivative of my ith plus 1 interval at xi. Once again, put mathematically, here we have 2c plus 6di, xi plus 1 minus xi must be equal to 2ci plus 1. So this is going to give us 4n minus 6 equations if we take all these equations out. However, we're 2 equations short because we have to have 4n minus 4 equations to perfectly solve out for all of our unknowns. In other words, these coefficients. Therefore, we need to deal with what's happening at the endpoints, just like we did for a quadratic spline. However, unlike the quadratic spline, there's more types of choices that we can make. In the end, we're going to have 3 choices that we're going to consider. Natural splines, shown here as this curve, where we assume that the second derivatives are 0 at the endpoints. So the second derivatives must be 0 here and here. We can have what's called a clamped end condition, where we assume that the first derivatives and the last the first derivative at the first knot and the last knot are known. In other words, we're going to say, we're going to pick what the first derivative value is here and here. As a general pick, they're generally selected to be 0. But you could pick any value that you want. So this is called clamped, because we're going to fix that first derivative in place and force it to be some number. The last value is called not a knot end condition, which is going to force continuity of the third derivative at the second and penultimate points. In essence, this is going to mean that these are not really considered knots, but they're still forced to have the function fit into them. We can put this into mathematical terms. If we pick the natural spline, the natural cubic spline, we end up having C1 is 0 and Cn is equal to 0. We're going to go through how we end up with these general first parts of the equation, but I'm going to sort of skip ahead. When we use a clamped spline, we know the first derivative in this, the first derivative of the first interval is going to be fixed at some value. So that ends up going in here as a fixed number. And then the set first derivative of the nth point is also fixed, and that goes in to this equation here. In terms of not a knot, we end up with these 2 equations that are going to fill in our entire set. So let's start building up our equations. It's going to follow quite closely to that of the cubic spline, but we're going to end up with a little shortcut. So here I've summarized the points. We have our first condition, which is going to hold in this equation. The second condition on continuous first derivatives is going to give us the second set of equations, and then my interior continuous second derivatives are going to give us this end condition. We can take advantage of a trick using pre-substitution and pre-solving for some of our variables to make our linear algebra easier. So first we're going to determine an equation just using the c's at the interior points. First, we're going to look at our second derivative equivalency. Remember, this said 2ci plus 6di times xi plus 1 minus xi was equal to 2ci plus 1. I can divide through by 2 to get this equation here, which I can then solve for d. I can take this d equation and substitute it into the first criteria, which, if you remember, says si xi plus 1 must equal si plus 1 of xi plus 1. Remember, that was that long one. When I plug that in, I get this equation here. I can then take this and further back substitute this into my requirement of having a continuous first derivative at each interior point. Remember, this was the equation si derivative of xi plus 1 equals si first derivative I plus 1 times xi plus 1. And I can plug both of these terms into that equation and rearrange and get this form. This is very useful because what you'll notice is I have only c's in this equation and constants. Remember, the fi's are known, and each hi is xi plus 1 minus xi, right? It's that interval over which we're moving. So all of the points are known in here, aside from those different ci's. And not only that, but these terms give us a tridiagonal matrix because I have ci minus 1, ci, ci plus 1. We should expect to see this nice tridiagonal banded system. Let's assume that we're going to use a natural spline, remembering that we set the second derivative equal to 0 at each endpoint. This means that C1 equals 0 and Cn equals 0. In this case, we can go in and make our linear algebraic equations. Here we have that 1 for that C1 equals 0 equation by putting in a 0 here. We can take in that other end fixed point where we have 1 Cn equals 0 down here. And then we can fill in the chart. In this case, each column gets the h of I minus 1. Then we get this 2hi minus 1 plus hi term, and then h2 term. And we can put this all the way in going down. And then in our, what we sort of normally call, say, our b vector, we have this term of 3f3 minus f2 over h2 minus f2 minus f1 over h1, right? And so this gives us a very nice pattern that we can follow when building this matrix and b vector for solving the problem. Once again, once we have this system built, we can go in and use one of our tridiagonal solving problem solutions, either with, say, MATLAB or by hand or with our own built-in functions. I now want to apply a cubic spline to solve the same problem that we've used as examples for our linear spline and our quadratic spline. Once again, that's finding a value for this these set of data points at f equals 5. Once again, we have our values of x and f of I, sorry, x and f's, and we need to identify which interval we're going to work on. Once again, we're working in the second interval because it's between pairs 2 and 3. So now we're ready to start setting up our equations. I'm just going to draw forward our definition of the matrices from a cubic spline from the previous slide. So we can go in and we can start looking at each of our functions. So remember, we can write out our different f values. These are just coming from over here. So f1 is 2.5, f2 is 1, f3 is 2.5, and f4 is 0.5. Then we can calculate our h's. So our h1 is our second value in x minus the first value in x. So 4.5 minus 3, that's 1.5. We can write this out for h2. And then we can write this out for h3. So that's 9 minus 7 is 2. Now we're ready to go in and start solving these equations out. So based on the previous slide, we can fill in these equations. So remember, there's a 1 here. We have the term h1. So remember, that's 1.5. We have the next term in here is twice h1 plus h2. So that's 2 times 1.5 plus 2.5. Then we have h3, which is 2. Now we get some zeros. We can add in the appropriate zeros here. Now we have h2, which is 2.5. We then have twice 2.5 plus 2. Then we end up with h3, which is 2. And then we can do the last row, which has all these zeros and then a 1. Okay, then we have C1, C2, C3, C4. And then I'm going to have to put some stuff down here because I've run out of space. So now it's going to be the right-hand side. So this is 0. We have the term 3 of 3 times f3 minus f2 over h2 minus f2 minus f1 over h. This ends up being 4.8. We can then do the same thing. So 3 f4 minus f3 over h3 minus f3 minus f2 over h2. We can do this all out, and then this gives us negative 4.8, and then finally a 0. So we can then use MATLAB to come in here and calculate all this out. I'm going to just put them maybe over here, and I'll use a different color. So if I do this, I have C1 is equal to 0, C2 is equal to 0.83954, C3 is equal to negative 0.7665, and C4, of course, is 0. Okay. So once this is built up, we can solve it, and then we end up with all of these C equations. Once we have our C equations, which I've copied over here and typed them in with a few extra digits, we can go back and start filling in our other equations. Remember, we used this equation for back substitution earlier. We can now use the C values that we've already calculated to calculate these different equations. And then once we get, we can do the same thing for our B's. So when I do this out, I have B1 equals negative 1.419, B2 equals negative 0.16, B3 equals 0.022, and then I can apply this to my D's. D1 is 0.1865, D2 ends up being negative 0.214, and D3 is 0.1277. Right. So this now gives us all of the information that we need to build our cubic spline. So I'm not going to write this out because we'll be here for days, but I can take each of my spline intervals, so interval 1, 2, and 3, plug in the numbers from the previous few slides, and we can have our equations. Once we do that, we can solve for where x equals 5, remembering that x equals 5 sits on this in this second interval. All we need to do is plug in 5 for the x's in this equation, which I've done down here. When I do this all out, I get 1.103. This is the end of what I want to cover with splines. Next, I want to cover relatively briefly lookup tables using splines within MATLAB and some other piecewise interpolation schemes. Lookup tables are used routinely in computational approaches. The simplest type of lookup table will do exactly what it may sound like. Given a series of x's and f of x's, it will tell you, it will go through and find the appropriate f value. So let's say I said, what's the f value at 4.5? It should go through, identify this indices as belonging to 4.5 in the x, and return 1. This seems trivial if I have, say, 4 numbers or 5 numbers to look through. But it's very common to have hundreds or thousands or even tens of thousands of data points that one might have to look through. This is tedious, if not impossible to do. This is tedious, if not impossible to do by hand. So we often want to use lookup functions. In the simplest lookup function, we're not going to employ any sort of interpolation. We're just going to do simple look to see if things match and then report this data. More complicated lookup functions might go through and identify that the data sits between these 2 points and then do an appropriate interpolation between the two. We'll leave that to you to do for practice. How my lookup function is going to be structured is shown here on the left. Here I could have, say, a function named lookup. I'm going to take in my series of x's, my series of known f of x's, and then the value that I'm going to look up. I then march through each of the values in my lookup table, so each of the indices through here. I then do an if statement to check to see if the f given, or the x given, is equal to my current iteration of xi. If it is, I use f equals, the return value f is going to be equal to the f array at that individual index, and then I stop that search. Right? So this is going to be the simplest version of a lookup table. More complex ones may start doing interpolation between looked up values. Or if you had 2 dimensions, they can get even more complex. Next, let's talk about our piecewise interpolation via MATLAB. So remember that splines are a special type of a piecewise interpolation, right? I'm using data only over a specific set. The simplest version in MATLAB is our spline. When you type in spline, this is going to give us a cubic spline. Once again, we're going to feed it in values of x, an array of y, and then this third column, this third entry is going to be the x value that we're looking up. The key thing is that what's going to happen is going to be dependent on the number of data points in y. This is going to tell us if the cubic spline interpolation is going to use not a not condition. So this is the case when the length of y is equal to the length of x, this gives not a knot spline. And if the length has an extra 2 values compared to x, it reports clamped spline. In this case, when it's clamped, x1 is the derivative at the first point, and yn is the derivative at that last point. So we can implement this in MATLAB. Let's just take an example written out here. We can say take a line space of 10 points. We can then say put in some sort of function. And then we can calculate many points, say 100 points in this model using not a knot interpolation. In this case, we have our xx values, so the values that we want to get out over these 100 points. We can put them into Spline. Now all these values are stored in y. We can then implement this in MATLAB using a few select points along this line to sort of orient ourselves, and we can get these data points. The spline function is shown as our solid line in this case. I'm including in here a dashed line that's going to show a different functional piecewise interpolation called Runge's function, which we're not going to discuss. We could do the same thing if we wanted to do a clamped function. In this case, let's say that we want that first derivative, the first derivative at the first point to be 1, and the first derivative at that last point to be -4. In this case, I need to expand my y data set to include that information. So I can still get that y, say, data points, and then I just add in the front and in the back what I want my clamped value to be. After this, I'm going to just go through the exact same process that I did previously, where I can generate lots of points using linspace for the points that I'm interested in finding. And then in this case, I use this y clamped version, which has these 2 extra data points. When I go ahead and plot this all out, we'll notice that I end up getting these oscillations at the end in comparison to the Runge's formula. I will note that if you were to draw a line, sort of a tangent to that curve by the first point, it looks like a x equals y line, right? So a line with a derivative of 1. This is exactly what we expect based on this one here. Conversely, if I look at the last data point, we have a relatively sharp tangent line moving downwards. This is going to represent be that slope of -4 over here. So this gives us a way to control, the clamp function is going to give us a way to control this. Usually we don't want to fix it to say -4 or 1, which may supremely bias it and lead to oscillations on the side. But it does serve as a nice example. The spline function in MATLAB is only going to return a cubic spline. MATLAB also has a function called interp1, which will form different types of splines, different types of piecewise functions. It's going to work relatively similar to the spline function, where I provide an array of x's, an array of y's, and either a single value or multiple values xi where I want my interpolation to occur. I then need to include a fourth term, which is a string, which tells MATLAB what type of method to include. Here I could do our linear, which is going to be a linear spline. I could do just regular spline, which will return not a not cubic spline interpolation. Or I can do several other types of interpolations. One being nearest, which will just return the nearest value of y. It will return the value of y of the nearest point x. I'll show you what this looks like in a second. We can also use p-chip or cubic, which is going to be a piecewise Hermite interpolation. I'll once again show you what this looks like on the next slide. So this interp1 is going to give us more control over what type of interpolation we have. This 1 is going to be here because this is going to be a one-dimensional interpolation. I'm only supplying one set of x values. Let's take a look what these different interpolation methods might look like. So the linear response, that's that linear spline that we had talked about way at the beginning of lecture. It looks just like we had sort of expected. The nearest neighbor case forms this staircase looking like spline. Here, it's more of a step function, right? We either get the value of the previous point or the next point, depending on how close we are to it. We can do our regular not a not spline, which is shown here. And then we have our p-chip, so our piecewise cubic Hermite interpolation. This is going to give a similar response to a spline, but it's set so that the second derivatives of the function are not necessarily continuous at each individual point. However, the first derivatives are approximately equal to the first derivative of the spline. In this case, we end up getting shape-preserving behavior. If you notice, at this point, we have sort of this staircase-shaped curve. So we, in essence, eliminate these oscillations between these points that are at roughly the same values. So we can help prevent oscillations when we have scattered data. However, if we have very smooth data, which would fit very nicely in maybe a quadratic fit, it may not work quite as well as a regular spline. The last topic that I want to touch on briefly is multi-dimensional interpolation. In this case, we're not trying to interpolate just along, say, the x direction to get f of x, but we have maybe 2 dimensions to work. Let's say we know x, we know y, and we want to interpolate what fxy would be. In this case, we can perform multiple interpolations. So first, let's go down here as an example. So in this case, we would first interpolate along x to get our new xi. And we would do that for both y1, a set of y points, for one y point, and then the next closest y point. So we can interpolate on both sides here. This would give us xi at y1 and f, maybe I'll write that bigger, f at xi, so our interpolated x with our known y up top, f at our interpolated x at our known second point at y. Then we can do interpolation along the y-axis, where we keep the x constant here, and then do an appropriate fit along that y case. We can do this using any of the methods that we've talked about today, whether that be splines, Newton or Lagrangian polynomials, just appropriately done in one dimension. We interpolate on one dimension first, and then we interpolate on the second or third or fourth dimension successively. I've written out here the case of the Lagrangian form. You'll notice that we have x terms and y terms here. And we first look at the x's, the old constant x's, the new pairs of, so x1, y1, x2, y1, x1, y2, x2, y2. So we have to have terms hitting up all 4 points on this corner around this central point. The nice thing is that MATLAB has a built-in function that will do our interpolation, multi-dimensional interpolation for us. Once again, we're going to use an interp function, but now instead of interp1 for 1D, we can have a 2 or 3 to represent 2-dimensional or 3-dimensional interpolation respectively. In 2 dimensions, we have both our set of x vector, y vector, and then the z vector, so that f of x, and then we give it the x and y points that we want to query, and then the method. Once again, we can use those same methods that we had before, nearest, linear, spline, p-chip, or cubic. Same thing with 3D interpolation. This time we have one extra vector reporting the f of x, y, and z, and then we have 3 variables that are going to determine the point that we're querying. With this, I want to close out. As a quick review, we've talked about what splines are. We've talked about simple splines, or linear splines and quadratic splines. Then we went to the more complex cubic case, which required us to select an end type, being either natural, clamped, or not an end condition. We talked about simple lookup tables and then how we can use built-in MATLAB functions to calculate interpolations for us in MATLAB. Lastly, we talked about multi-dimensional interpolation, where we said we would interpolate along each dimension known at a time to build up that multi-dimensional interpolation. All right, see you in class.